Welcome to today's central exercise session in Mathematics 2. As usual, your questions are highly welcome on our chat channel that you'll find on chat.tum.de. And please use this channel here, MA9714-CE. And as usual, the chat will be moderated by Eileen Carlson. So we'll be discussing sheet number 13 today. And sheet number 13 is about line integrals over vector fields. So the first problem here, C13.1, is concerned with a vector field over different lines, this one and this one, and we will compute the integral over those. And the second problem, C13.2, is concerned with Green's theorem. That provides a kind of a connection between volume integrals and line integrals in vector fields. And we're going to see an example for how we can use this connection here. So let's start with 13.1. So in this problem, we are given points A and B in R2. And we are given two curves, and the first task is to provide a parameterization for those curves. Let's make a quick sketch first. So basically the points that we have are these here. So here's x1, here's x2. And we have here the point that's called A, point 1, 0. And the point minus 1, 0. That one's called B. And we're considering two different curves. In A, we are considering the curve gamma 1, that is a straight line with endpoints A and B starting at A. So gamma 1 will be this curve here. Oh, let's make that a little. Going in this direction, right? From A to B. And the first task is to come up with a parameterization of gamma 1. And for a straight line, it's usually easy to come up with a parameterization. What always works is to use the convex hull of those 2 points and parameterize that. So what we can do, for example, for gamma 1 is to use the parameter space from 0 to 1. And then the curve maps to R2, of course. And we just define gamma 1 of t as t times the endpoint plus 1 minus t times the starting point. So for t equals 0, that will be 0 times b plus 1 times a. So t equals 0 corresponds to this point. T equals 1 would be b plus 0 times a. So t equals 1 corresponds to this point. And in between those two, we're basically what we do is we reduce the amount of A that we are using and increase the amount of B that we're using. So we're moving on the line from A to B linearly. And of course, there's other parameterizations that you could also use here. Yeah, basically everything that yields this line will work. Okay, so that's one possible parameterization. And let's use the coordinates here. And then we get t times minus 1, 0. That's b plus 1 minus t times a is 1, 0. So altogether we get, let's see, minus t plus 1 minus t. So that's minus 2t plus 1. And a 0 for the second coordinate. Okay, and as I said, that's one possibility. There are numerous other possibilities that will also work. Possibly will give you different results, though. Okay, so that's a parameterization for that straight line connecting those 2 points. Any questions so far?
No questions so far.
Great. So let's have a look at the second parameterization, part B. So here we're considering the curve with endpoints A and B, again, starting at A, that corresponds to a line along the unit circle with x2 greater or equal to 0. So we're using the unit circle in this upper half of the plane, not the part below here. Okay, and that means, well, if we're moving along the unit circle from A to B, then that will be like this here, basically. And we're moving in this direction, so counterclockwise. Okay, and that is the curve gamma 2. And you do know parameterizations of the unit circle. Again, we just choose one that is easy to handle and that does the right things. So what we want to do is we want to move in counterclockwise direction. So the usual parameterization would then be to use gamma 2. I'll add the parameter interval in a second. So the parameterization will be something like cosine t sine t. The radius is 1, so we don't need to do anything about that. And we're moving from this point here, 1, 0. That corresponds to an angle of 0. And then we increase the angle up to pi. So that means our parameter interval goes from 0 to pi. Right? Pi corresponds to this point here. 0 corresponds to this point here. All right, so that's the parameterization here of gamma 2. Any questions about that?
Nope, still no questions.
Wonderful. So then we're going to compute a line integral over a vector field, and the vector field given is R2 to R2. And it's given as V of x1, x2 is defined as x1, and then x1 squared plus x2 squared. And the question is to determine the line integrals of V along the curves gamma 1 and gamma 2. So we need to compute 2 line integrals here. So let's start with gamma 1. So the line integral over VDS along gamma 1 is simply defined as the integral over the scalar product of V evaluated at gamma 1 of t with the vector gamma 1 dot of t, so the derivative of gamma 1 dt, and we're integrating over the parameter space, and that was t from 0 to 1 in our parameterization. So remember the parameterization that we got here was this. So let's just copy that. Okay, so here's our parameterization once again. That was gamma 1 of t. So what do we get for the integral? Well, first part is this V of gamma 1. V is x1 and x1 squared plus x2 squared. So if we substitute this for x1 and this for x2, then what we get is minus 2t plus 1. That's the first coordinate. And then minus 2t plus 1 squared plus 0 squared. Right, so that's the first part of our scalar product. And then we multiply this one, or the transpose of this vector, with gamma 1 dot. So we need to compute the derivative of this vector here. And that is given by minus 2 and 0. Okay, so what we get here is the integral from 0 to 1 over, let's see, that would be 4t minus 2 dt. And that's easy to integrate. The integral of t is t squared over 2. So 4t is 2t squared then, minus 2t from 0 to 1. So upper bound is 2 minus 2. And lower bound is 0 minus 0. So that's 2 minus 2, and that is equal to 0. So that is the integral over this vector field along gamma 1. Questions about this one?
No.
Nothing so far. Wonderful. So let's have a look at the second one, gamma 2. It's pretty much the same thing. So we compute, VDS along gamma 2. Again, let's maybe copy that vector field definition. Copy that one. And also gamma 2. Gamma 2 was this curve here. Okay, so that's the information that we'll need. And then again, this integral is defined as the integral over the parameter space. In this case, the parameter space is from 0 to pi. And we need to compute the integral of v of gamma 2 of t, scalar product with gamma 2 dot of t dt. So this is equal to, let's see, v of gamma 2. So we have x1, that's simply the cosine of t here. And then we have x1 squared plus x2 squared. So that's cosine squared t plus sine squared t. And we need to multiply the transpose of this with the derivative of gamma 2. So computing the derivative of this one, the derivative of the cosine of t is the negative sine, and the derivative of the sine is the cosine. So what we get here is, again, from t to pi. So here we have cosine t times minus sine t. So that's minus sine t cosine t. Here we have cosine squared plus sine squared. That's a 1. So we have 1 times cosine t. That's simply plus cosine t dt. And then to integrate this sine cosine, we can use numerous techniques. One possible technique is suggested in the problem statement, and that says use the following trigonometric identity. Sine t times cosine t is equal to 1 over 2 sine of 2t. And if we're using that one, then the integral becomes t from 0 to pi minus 1 over 2 sine of 2t plus cosine of t dt. And that can now be integrated elementary. So the integral of the negative sign is the cosine. So we get something with cosine of 2t. If we take the derivative of that, we get the negative sine of 2t times 2. So we need to get rid of the 2. That means we need to divide by 2. And together with this minus 1 over 2, the factor that we will get is 1 over 4, right? So minus, and the minus we get by integration, those cancel out. So we get a plus here. And for the cosine, the antiderivative of that is simply the sine of t. and that from 0 to pi. So for the upper bound pi, we get cosine of 2 pi, that's 1. So 1 over 4 times 1. Plus the sine of pi is 0. Minus the cosine of 0 is also 1. So 1 over 4 times 1 again. And the sine of 0 is again 1, sorry. So that's 1 over 4 minus 1 over 4, and that's a 0. So same value for the integral, and we again get 0 here. So questions at this point?
Yes, so there's one question. Do they have to know this formula sine t cosine t is equal to 1/2 sine 2t by heart, or will they be provided with it on an exam?
This one, no, you wouldn't have to know this, no. I will provide you with that if it may make sense to use it. And of course, it does not mean you have to use it, but depending on the way that you use it, might be a clever idea to do so.
Okay, that was everything.
Good. So now let's go to D. Final question on that problem. Is V a conservative field? What that means is there a potential, a function that has V as its gradient field? And well, the first thing that we could ask you is, does it behave like a conservative field so far? And for a conservative field over a simply connected region, and R2 is of course simply connected, we would expect that the integral over any curve doesn't depend on the curve itself, but just on the endpoints. So here we have two different curves, but the integrals that we computed have the same endpoints for those curves. So if the field was conservative, we would expect that the integral values along gamma 1 and gamma 2 would be the same. And this is indeed the case here. So if those were different, you could already exclude that possibility, right? At that point, you could make the statement that, well, obviously the integral doesn't just depend on the endpoints, it depends on the curve itself. So it cannot be a conservative field. But that's not the case here. So we have to investigate further. And the next criterion that we have is the integrability conditions to see if that is a conservative field. And remember, basically the integrability conditions mean that the Jacobian of the field is symmetric. The Jacobian of the field corresponds to the Hessian of a possible potential. So that would mean the Hessian of the potential is symmetric. And you would expect that for a C2 function, right? So if there is a potential, C2 potential, then those mixed second order derivatives have to be the same. And the second order derivatives of the potential would of course be the first order derivatives of the coordinates of the vector field. So what we do is we just compute those and see if those so-called integrability conditions are satisfied. Integrability conditions, right? And those would state that all the mixed derivatives agree. In this case, we are in dimension 2, so there's only 2 possibilities to mix those. So we have to have a look at dv1 dx2 and dv2 dx1 and see if those agree. And if they do, and the domain is simply connected, then that means the vector field is conservative. So there is a potential. If they don't, there cannot be a potential, no matter what properties that domain has. Okay, so let's have a look at those. Again, the vector field V, we have that here. Let's copy that once again. So here's our vector field. Let's just compute dv1 dx2. So that means we need to compute the derivative of x1 of this part here, with respect to x2, and that is obviously 0. And for dv2, we need to compute the partial derivative of this with respect to x1. And well, that is 2x1. Right? So obviously those do not agree everywhere. And that means the vector field is not conservative. The integrability conditions are not satisfied. Okay, so the vector field V is not conservative. And remember, the inverse only holds over a simply connected domain. So if those were satisfied, we would still have to see if the domain is actually simply connected. And of course, we'd have to include a statement to that effect in our solution. And then we could conclude that V is conservative. Or of course, another approach would be to simply try and find a potential and see if that works or not. Okay, but usually integrability conditions are easier to see because you just need to differentiate. You don't need to integrate anything. So the fact that we got the same integral value before is mere coincidence. Good. Any questions?
Yes, there's one. Could we also check if there is a potential with the condition rotation of V is equal to 0?
So basically, the rotation is something that I think we only defined for R3, right? I'm not quite sure if I'm confusing those now. I hope I don't. I think we only defined that for R3, and that's the one that's only defined for R3, right? Divergence is universally defined, and rotation is only defined in 3-dimensional space. So we can't use that here. This is a 2-dimensional vector field. So you could use that on 3-dimensional vector fields, and then the rotation basically is the vector that just lists those mixed derivatives that we need to investigate. So that's where the condition with the rotation comes from. But remember, you can't use that in R2. You can only use that in R3. So usually it's easier to just go this way here. I find the formula for the rotation not that easy to memorize. Yeah, if you like that better in R3, of course, you can do that.
Okay, that was it. Don't have any more.
Good. So then let's have a look at Green's theorem, 13.2. So here we are asked to again compute an integral over a vector field, given like this here, along a curve, and that curve is now defined as the boundary of a triangle with these vertices in counterclockwise direction. So that's C13.2. Maybe let's start with a sketch again. So sorry, that's x1, of course. That is x2. So we have a triangle here. The vertices are the origin, 0, 0. Then there's 1, 0. And then there's 1, 2. Right, so here's the origin. Here's 1, 0. Oops. 1, 0. Here's 1, 2. And here is our triangle. Okay, so that's B. And the curve gamma is defined as the boundary of B in counterclockwise direction. So basically gamma is, gamma is that orange line here in counterclockwise direction. That means we're moving in this way. Right, so this here is gamma, and maybe let's color B differently. So B is the whole domain here. So that's the triangle B. Okay, and the problem statement already says use Green's theorem. So that's what we're going to do. Of course, you could also compute that in an elementary fashion by just parameterizing those three curves and then computing the line integrals as we just did in 13.1. But probably the approach that Green's theorem provides here is a little easier, because remember what Green's theorem does? It connects a line integral over a vector field along this gamma, and this gamma is again the boundary of that B here, with the volume integral of a certain expression over B. And that expression is dv2 over dx1 minus dv1 over dx2, dx1 x2, right? So if B is a domain that we can easily describe, and if this expression is not too complex, then this integral is probably easier to compute. On the other hand, if B as a domain is not very easy to describe, but maybe its boundary has a nice, easy parameterization, then it might be much easier to compute this integral here, right? So depending on the setting, Green's theorem gives you any direction you want. Yeah, you can compute one integral from the other if that turns out to be the easier way. In this case, this triangle B here, you will hopefully see that this can easily be described as a normal domain. So this B here is the set of all x1, x2 in R2, one with the following property. X1 is obviously between 0 and 1. Here, that's bounded by 0 and 1. And x2 is bounded by 0 below, and this line here, so a function of x1 above. So we can write that as 0 is less or equal to x1 is less or equal to 1. And 0 is less or equal to x2. And where that line here, that simply is the line through 0. And remember that point here has an x2 coordinate of 2, an x1 coordinate of 1. So that is the line x2 equals 2x1. So that is the upper bound here, 2x1. Any x2 coordinate below that line belongs to the triangle. So that's the description of B as a normal domain. So this integral over B, the volume integral, shouldn't be too complicated. All we need to do is compute this expression here. And well, that's exactly what we do now. The vector field V of x1, x2 is given as, let's see, x1, x2, and x1 squared, x2 to the power of 3. So dv2 dx1 minus dv1 dx2 is equal to, let's see, v2 is this expression, and differentiating that with respect to x1 yields 2x1 times x2 to the power of 3. And v1 is this expression, and differentiating with respect to x2 simply yields x1. So this is the expression that we need here. And one more thing we need to check is the direction. So the this curve, of course, has a direction, and that needs to be oriented such that the domain B is located to the left of the curve. So as we move along the curve and look to the left, we're looking into B. And that is, of course, the case here. We're moving here in this direction, we're looking to the left, and we're looking into B. same here, and same here. Right? So this B here is to the left of gamma. That's given as gamma is counterclockwise. If that was not the case, we have to change the orientation of the curve first. Okay, so B is to the left of gamma, so that means Green's theorem can actually be applied. And well, let's do that. So this integral over VDS along the boundary of B, that is equal to the integral over B of this expression. So that's 2x1 x2 to the power of 3 minus x1 dx1 x2. And then we use the description of B as a normal domain. So x1 is bounded by constants. That's going to be the outer integral. x2 is bounded by functions of x1. So that's going to be the inner integral. So we have x1 from 0 to 1 as the outer integral, and x2 from 0 to 2x1 as the inner integral. 2x1 x2 to the third minus x1 dx2 dx1. Right, and that's just the polynomial, so that shouldn't be too hard to integrate. Let's see, integrating this with respect to x1. So here we have, x2. Here we have x2 to the power of 3. Integrate that and you get x2 to the power of 4 over 4. Here we have a 2, so it's 2 over 4 or 1 over 2. x1, x2 to the power of 4. And here we simply have a x1, so integrating that with respect to x2 yields x1, x2. Boundaries from 0 to 2x1. So let's substitute the boundaries. And we get, let's see, upper bound first, 2x1 for x2. So we get 2 to the power of 4 times x1 to the power of 4 times x1. That's x1 to the power of 5. And that was 2 to the power of 4. And here's a 2 to the power of minus 1. So altogether, that's 2 to the power of 3. And then here we have minus x1 times x2. So that's minus 2x1 squared. And the lower bound, x2 equals 0, well, that yields a 0 here and a 0 here. So that's simply minus 0 dx1. And let's compute this integral. So integrating this with respect to x1, we get, let's see, 2 to the power of 3, x1 to the power of 6 over 6, minus 2 x1 to the power of 3 over 3, x1 from 0 to 1. Here we can cancel out a 2, so that's 2 to the power of 2 over 3, or 4 over 3. And then substituting the bounds, we get 4 over 3 times 1 to the power of 6, that's just 1, minus 2 over 3 times 1 to the power of 3, again, just 1, minus 0 for the lower bound. So the result here is 4/3 minus 2/3, that's 2/3. Okay, and that's the integral that we get here. So, any questions about this one?
Yes. How would we have to compute the integral over B if we had more than 2 functions in the vector field?
What do you mean by more than two functions? A higher dimensional
That
vector
they have,
field?
yeah, it would be my guess.
With all that you know at this point, you would have to do this in an elementary way. So Green's theorem only holds in the planar case, only for two-dimensional vector fields. There are generalizations, but we didn't cover that.
And you probably won't be asked that on the exam. Right?
I won't ask it on the exam. No, if Green's theorem comes up on the exam, then it's going to be a two-dimensional vector field. And if it's not two-dimensional, try something else. Green won't help you.
And then there's one, how do we make sure that B is always to the left of the curve? Couldn't we simply change the direction of the curves and everything else would remain the same?
Well, if you change the direction of the curve, then of course the parametrization would be different as well, right? So you'd have to do some changes here. So basically, the question is how is B connected to the curve? And B needs to be compact, so bounded and closed, and to the left of the curve. So you need to take the curve that is in the right direction. Basically, you need this curve here for Green's theorem to hold. If you're moving in the wrong way, then Green's theorem would refer to, so if you're moving this way, the theorem would refer to this outer part here, and that is obviously not bounded anymore, so the theorem doesn't hold. Right? You need to make sure to get the right direction of the curve.
And how do they make sure of that? You need to be careful when you write down your parameterization.
Yes. Be careful when you write down your parameterization. Look at the curve thoroughly.
And it really matters.
It does matter.
Okay, that's what I see so far.
Okay, well, that's all I have for today. So if there's no more questions, I guess we can close that session for today. And that means this was officially the last central exercise session of this lecture, and probably the last central exercise session in mathematics of your whole life. I would say see you at the exam, but unfortunately, I'm not going to see you at the exam as it's going to be online. So there's probably not a good chance that I'll meet you there. Yeah, maybe I'll see you at some other event in the future. Hopefully. What you can do if you want to meet me once again is join the tutorial sessions on Thursday, of course. You won't meet us in real life, but you'll still meet us there, at least virtually. And if you have any more questions, of course, you're welcome to ask there. So as usual, tutorials take place on Thursday from 2 o'clock to 5 o'clock. And that's going to be pretty much the last chance to ask any questions before the exam comes up. Other than the Moodle forums, of course, we'll make an effort to answer questions that come up there. But as the exam comes closer, we probably have different things in mind. Most notably preparing the exam. So if you want to ask questions, be sure to ask them a few days ahead of the exam so you can still get an answer. Okay, so thanks a lot to Eileen for moderating the chat this time and for the whole semester. It was a big help. Thanks for attending. I hope I'll see you on Thursday, and otherwise, good luck for the exam.